Good morning, everybody. So, as you mentioned, we'll be talking about highest quality. Everyone says higher broadcast. We just say highest. It's more compelling, I guess. So, I should probably start the presentation here. Let's see, does that work? Pardon me, some technical difficulties. Yeah, I can't get it to go over there.
Where did my mouse go?
Sorry guys, just a second. It's my third presentation of the week and somehow I forgot how to use PowerPoint, so.
We've had a little bit of trouble with this laptop here.
If you slide PowerPoint over to the other screen. You guys will see the secret sauce.
And then it disappears.
Yep.
Great.
Oh, no, that try it now.
Now let's try it then.
There we go.
Great.
All right. Sorry about the delay on the delay. Oh, hold on, I broke it again. So I can't have it full screen is the problem. I got it. All right. That's fine. All right. So, in order to tell you about what you can do with highest speed video over internet, we got to see where we've been. So everybody remembers 1980. Everyone here is old enough to remember that. Empire Strikes Back, Pac-Man. Oh yeah, TCP/IP. We'll talk about that in just a minute. 1982 is when that became common. Of course, the original Mac, 1984, and Miami Vice, right? Oh, and some streaming came along in 95 and 95 for Shockwave. So we all remember these, right? Very, very good tools. In fact, they all have something in common. They were the newest and the coolest out there. They were the best at the time. Everyone accepted them, even Miami Vice. And they allowed to grow into future releases. Star Wars, OS X. Oh yeah, some of them had awesome outfits. And nobody could beat any of those at the time. Mac was the best platform out there. TCP/IP was the best tool out there. Empire Strikes Back was the best movie out there. But none of those are really great now, 30, 40 years later, right? And none of them are really useful. I mean, it's cool to watch Empire Strikes Back, but you won't be caught dead watching Miami Vice on Netflix, right? So why is TCP still used? Right? Why do we still use that? It's because it's prevalent. It's the backbone of the internet, right? UDP is the same way. We can still do UDP. You can do video over UDP. Transport stream is one example. RTP is another. And they work really well, but not great for streaming to worldwide audiences. So there's got to be a better way. So today you have really two options for the internet transport. You have TCP, one-way TCP like HTTPS, and two-way, with feedback and control, RTMP, RTSP, dash, etc. And you have UDP, which is send and forget. Toss it over the fence, hope it gets there. Now you can have it with FEC, and that adds additional overhead. So your 10 meg stream is suddenly 12.5 meg. So there are transfer challenges with this, with moving any data, whether it's streaming video, loading something to YouTube, or even sending a large email with an attachment. The size of it, how fast you can get it there, and how much control you have over that transport. So TCP was great 40 years ago because it was what was available, and it actually worked really, really well because data wasn't big then. Today data is big. This presentation at H.264 is going to be a gig, maybe a gig and a half, right, for a 30-minute presentation. You have different types of networks. Back when TCP/IP came around, there was barely dial-up modems. It was all internal on Token Ring. Now you're on your phone, you're watching it on a plane, which is just a miracle in and of itself, right? Global, everything's global. We were talking earlier about the world feed for Times Square. Everyone around the world watches that. Of course, everyone here wants to see when Australia does it. Everyone in Australia wants to see when New York does it. So worldwide experiences are expected. And cloud computing, right? You're not just creating the content and sending it out from here to over to the next building or from here to the next state. You're sending it to the cloud. The cloud's doing CDN distribution all over the place. So what's the problem, right? The transfer challenge of all of that is TCP. It performs well under ideal conditions. This back chart here, I don't have a pointer, but the big yellow bar, that symbolizes TCP traffic in a LAN environment inside this building. You want to move 40 megabit per second 4K video around this building on the LAN, presuming PSAV lets you do it, you could do it easily without a problem. Just using TS over IP or RTMP. But it degrades with distance, right? TCP doesn't work over distance. It doesn't scale with bandwidth. You can't add more bandwidth availability to get better throughput. It just doesn't scale. And that's because of the increase in round trip time and packet loss. The further away from where you go, the more that increases, the slower TCP works, and I'll show that in just a minute. There are some alternatives out there to overcome this problem, but the bottom line is they all work around it. They don't really overcome it. So, a couple of words here. If throughput is the rate of successful messages delivered by the network, so think of 50 megabits per second, then goodput is the rate of useful information delivered by the network. So 50 megabits per second on a LAN, you're going to get a goodput of 50 megabits per second. 50 megabits per second over a compromised satellite network, you're going to get goodput somewhere in the neighborhood of 20 to 25 megabits per second. Any overhead reduces this. So you can add FEC, you can add retransmissions, you can do lots of different things to overcome this, but it reduces that output. So the goal is to maximize the goodput by minimizing the amount of redundant network data on the network. Reduce your retransmissions and get rid of error correction. Those are the two ways to do it. So let's talk about why TCP is so bad. And this is a little in the weeds, and I've tried to keep like 3 or 4 slides of these just to explain it. In fact, I need my cheat sheet in order to do this. But so what you're seeing here is the definition of network latency, right? And network latency is the time it takes to get from point A to point B. Every network in the world has latency. Sometimes it's imperceivable, but it's there. And that's because light or electrical signals take a certain amount of time to get there. Think about how long it takes to get information from Mars rover back to here. It's on a larger scale, right? So latency becomes the time it takes to get the acknowledgements for the TCP packet loss. And that's the problem with TCP, is it needs an acknowledgement. TCP is great. It acknowledges every packet, except it has to acknowledge every packet before it'll continue sending. So it has to wait that entire time. UDP, on the other hand, does not need to wait for the packet because there is no acknowledgement, except you don't know if it gets there. And then there's a sliding window, which is the amount of data that's sent while there's no acknowledgements. All right, so this is a lot of graphs to basically tell you that TCP works good on a LAN. So you see it ramping up the speed. Right, this is a graph. This is a speed graph. Ramps up the speed, and then at some point, right there, it drops a packet and it resets and it starts over. But because the latency is very low on a LAN, it can start over and go very fast. But on a bad network, this is the same scale. You have this problem where drop packets occur much faster, and so you can't get the TCP speed to get up, no matter what you do. Non-TCP transfers, UDP, look like this. They just flood the pipe, and they just keep sending packets. But these red ones are all drop packets. This is, I think, 1% packet loss. So this results in TCP playback being erratic at best. On the bottom is your bit rate, and the top and the left, the Y column is your percentage of playback rate. So look at two colors here. Just look at blue and yellow. Green is sort of off the chart. So at 1 megabit per second, TCP works fine until you get to even in the US, right? You're going to get 100% playback rate. This is number of frames per second you're really getting. Think of it that way. But if you go to 10, it's fine on a LAN right here, but even internationally, you're down to less than 10%. All right, so TCP unmodified, so no buffering, no simultaneous transfers, no redundancy. At 10 megabits per second, it works great in your building. Outside your building, you have less than 20% playback rate. HLS dash, which is what you guys watch on your phone, obviously compensates that by buffering heavily. That's why it's 30 seconds off at minimum. So Aspera came up with FastStream. Now, if you don't know what Aspera is, and I probably should have introduced us beforehand, we've been around since 2004 doing accelerated file transfer. We fill the pipe with good data, right? Good put is what we're all about. So at a gigabit per second connection, if you have 10% packet loss, we're sending it 900 megabits per second. So it becomes a math equation to send data. If you're shooting if you're acquiring at, say, DNX 145, 145 megabits per second, if you have a 150 megabit per second internet pipe, you can deliver in real time. That's the bottom line with Aspera's protocol. So we've modified that protocol to do streaming, particularly video streaming. And the reason we had to modify it is because in the file-based domain, we really want to get all those bits there in order, but because of packet loss, it sometimes doesn't happen. And rather than interrupting the transfer, we sort of stuff that drop packet in as soon as we can, but not right away, and we write it to disk. With video, that doesn't work. You need to get those packets there immediately. So we modified the protocol to support sending that retrans right away. But we only send it once, because the probability of missing, this is where this equation comes in. The probability of missing a second packet on a retrans is what this equation is about. And until you get up to over 300 megabits per second, that's an insignificant amount of time to drop a packet. So this explains that equation, and I won't go into too many details. If you want, you can come by the booth and we can talk about it some more after I'm done here. But the bottom line is, this is how we came up with the formula and the algorithm on how we use FastStream to send data and send it for live video without impacting the video itself. But we had to test it. So we did all this math. I didn't do any of it, actually. Our really smart development engineers did it. And then we tested. So we tested 3 bit rates, 6, 10, and 40 megabits per second, which were common at the time 2 years ago transmission rates. MPEG 2, MPEG 4, and then a contribution of 40 megabits. We did 100 transfers of 30-second videos over a simulated LAN of 200 milliseconds, 2% packet loss. That's Singapore to the US, so pretty far. And the end results were, at 10 megabits per second, we would drop make sure I'm looking at the right one. Yeah, we would drop a packet in just under 4 days. That's a packet, it's not a frame. And when you drop a packet, it looks like you're trying to update, you're doing a presentation. Would you like to update your computer? When we drop a packet, in a transport stream, for example, it could be nothing, you would see nothing visually, or it could be some blocking, or it could be you could have a freeze frame for a frame. It's really insignificant compared to all the other errors that could happen in a transport. So even at 40 megabits, which is full contribution from a venue, it's less than a day. I'm sorry, it's just under a day. So the probability of dropping a packet. So we put it all into a chart. This is a heat map of the results of our tests. The white is where packets are dropped. The lighter colors are where there was a possibility of a retrans. But only that one white dot right there in 10 megabits in all those tests did we drop a packet. So we did the same thing for TCP. We felt we had to do a real comparison to TCP because maybe what we had wasn't really that special. And so we did that again. And what we found was that we couldn't even get TCP working stable under those conditions until these times. And at that point, we gave up because these are unacceptable times to get a stream going. So again, at 10 megabits per second, it could take 25 seconds to get the stream stable to even start doing transfers. I'm sorry, doing video. Now again, this is unmodified TCP, right? So this is RTMP from Singapore to the US. And even after that, we found there was no guarantee of smooth playback because that was just till we got a stable signal, and typically we'd find the signal would drop off after a bit. So then we ran the math and said, let's see what we need to do for startup time. So startup time is the amount of time it takes to basically do a handshake. And once the handshake is established, it's real time. The added latency of a fast stream transport is 1.5 RTT. So in this test, it's 300 milliseconds is what we're adding in the transport. So 40 megabits per second, if you did a 2.5 second handshake, the probability of having a glitch an hour goes to 0. If you only give yourself a half second to start up, you're going to have a glitch. So we built this into the protocol, so when a session is established, we don't let the session fully establish until we have a good connection. Same numbers on 20. So if you look at the difference between 40 and 20, obviously it's a lot easier to get 20 megabits going than 40, and then even easier with 10, and I think, oh, I didn't do 5. So even at 10 megabits per second, on a bad wireless connection, so using a satellite or tethered phone, at 2.5 seconds, you still got a lock on 10 meg. So we took all of this, we created a product with it called Aspera for video, and it uses what we call fast stream technology underneath it, FASP. By the way, FASP is Fast Adaptive Secure Protocol. And we started doing some testing with it and giving it to customers to use. And what we found was they were very happy with it. This is an example of a test. So we've got an encoder on the left and some sort of playout device or disk on the right, or a re-encoder or something along those lines. And we're taking a source, for example, transport stream over IP, TS over IP, into our client machine and spitting it back out the other side of the server as the same thing. So if we're given TS over IP, we put out TS over IP. If we're given RTMP, we put out RTMP. What we don't do is change anything in the payload. We're agnostic to the payload. We don't know what it is. FastStream doesn't know what it is. It could be SD, it could be 4K, it could be HDR, it could be data streaming off of a log box. It could be anything. We don't touch it, we don't manipulate it, we don't do anything except move it from point A to point B.
John,
yes?
when was this done?
When was this done?
Yeah, when was this preliminary work complete?
So this was done in early 2014.
14.
Yep, so we came out with this in NAB 20, wait, it's 2018 now? 2016, sorry. Early 2016, because in NAB 2016 we came out with this and showed it to some big customers.
Yeah, I saw the demo of it. NAB, very impressive.
Thank you. So we had a lot of customers like this. This is great, except I need an HTTP source. I need HLS and dash. So we've gone further with this now, and we've created this FastBio, which is what we're showing at the booth today. And it takes native HLS and dash, pushes it through the gateway, and at the other end, the end user sees it as HLS and dash, and there's no difference, except that we're only basically showing the highest rate in the stack. So our demo is showing the same source with TCP as 1 megabit per second, 380 by 240, I think, and 360 by 240, and the fast stream through BitMoving's player at 4K, 12 megabits per second. Off hotel Wi-Fi, by the way. So obviously that gives a lot of advantages to contribution and distribution of live streaming content. Predictive, so again, this all presumes you have available bandwidth. If you're trying to push a 50 megabit per second stream down a 10 meg pipe, it's just not going to work. But assuming you have the bandwidth, predictability of the streams, regardless of the network, near zero startup delay. Marketing isn't letting me put in zero startup delay because they won't let me, but it's near zero startup delay, even on the worst connections. Lowest overhead, so again, no FEC, no error correction, it's all in the protocol. Simply the overhead is the packet loss. So if you're doing 50 megabits per second on a stream and you have 10% packet loss, which would be high, but if you had 10% packet loss, you need 55 megabits of bandwidth. No buffering, because we don't buffer. And the highest, so the second to last line is what we're showing, which is the highest possible rate from an ABR stack that's getting to you. And it works in all modes. So it works venue to venue, venue to cloud to cloud, stream to file, file to stream, internet, WAN, VPN, MPLS. So some use cases for Aspera. Transport, broadcast capture and play out, and contribution. The top graph is showing acquisition through a streaming server with bidirectional feeds to a production server. Think of this as a baseball game or a basketball game. And on the left, you've got your cameras and your disks and all your sources, and you're feeding all of them back to a broadcast center. And on your right is the broadcast center that's switching them, putting them, mixing them together, adding in the effects. But they're also sending you back at the bottom here the camera feedback for to the monitor so they can interact with the announcers. No, there was one more there. And then remote capture and delivery through like the phone over Wi-Fi to a server coming into a broadcast facility, and then distribution as well. So this was a live event we did a year ago. I had the pleasure of going to Havana, Cuba for a ballet. We were asked to support a international ballet event that was in Havana and produced by a US company. It was a goodwill mission and created on a Cuban government production truck, which was actually pretty impressive. It was a 30-foot straight truck, all HD, very nice gear. Using, I can't really call it public or commodity internet because that doesn't exist in Cuba. It was government run, but it wasn't a private line. It wasn't a fiber circuit. It was just, they gave me a port on some switch in a dark basement of this building. And using FastStream, we did 4.5 megabits per second to our Utah office where we handed it off to Akamai. Now you're asking why only 4.5 megabits per second? I had an 8 meg pipe. It was 175 milliseconds of latency and 15% packet loss. 15%. In fact, we did a SSH session initiation, and it took about 45 seconds to actually get that session initiated. But once it was initiated, it all worked. This bottom one here is an actual image I grabbed from my iPhone while on the 3G wireless in Cuba, watching it played back from Akamai, and it was crystal clear. And the reason that's important is because our contribution was of the highest quality we could get into Akamai. So that meant that Akamai could deliver the best quality to the end users. And even in Cuba, on my phone, it was less than 30 seconds delayed from live. So live events, content delivery and distribution, all works very well for FastStream. This is a use case I love talking about because I can now talk about it. This is Fox Sports World Cup coverage coming up this summer. They have 60 venues, I believe 20 cameras at each venue, and they're capturing them with a Telestream Lightspeed Live box at 220 megabit per second, 4 cameras per box. The math on that is 1 gigabit per box. That is going over public communications channels. It is not a dedicated circuit. There's a handoff in Germany, I think, and then it's all public internet all the way back to LA, where they are editing off of it as if it were live. It's writing to Omnion storage, and they're editing off of that and creating shows and highlights and bumpers. I'm happy to say this worked out of the box. There are 2 things we're doing with this. We're doing the 220 high res, and we're also doing a proxy at the same time, an HLS proxy that is going to S3 that then can be reviewed by anybody and people can make requests type of thing. This was originally tested in the States before they shipped it out, and the latency from live to edit in the States working directly off the Omnion without FastStream in it was 7 seconds. When you added FastStream into it, which included the round trip to Germany and back, it was 10 seconds, 3,000 milliseconds. So if you think about that, going all the way out and coming back over public internet, that's pretty good. So this is a real world use case. We're very happy to talk about it, as is Telestream, so feel free to stop by. We can talk more about this as well. And that is all I have until you have questions. Thank you. Do we have any questions? Yeah, go ahead.
When you said for the HLS and dash,
Mhm.
there is no buffer. Did you control the player behavior or?
So the question is, with HLS and dash, I mentioned no buffering, do we control the player? The answer is no, there's still the front-end buffering to make the HLS and the playlist. What we're doing is we're improving the quality of the connection between the player and the and origination, and the edge server rather. And so because that's an improved connection, you get the higher quality.
You mean the transport for buffer?
Correct. Correct. Yeah, you're not watching it and getting the buffering. You won't see that. Any other questions?
And do you have an SDK?
Do we have an SDK? Yes, we have an SDK. That's what we used for the bit moving player. That was a collaborative between us and them. We have a number of other partners working on the SDK. So that's all available, and SDK and Lightspeed Live as well. Any other questions? All right. Thank you very much. If you want to see us, come by booth 115. Enjoy the day, guys.